Let's talk about solving systems of differential equations using substitution. Suppose we have two interconnected 24-liter tanks of brine. That's a salt solution, A and B. Fresh water flows into tank A at the rate of 6 liters per minute. Brine flows from A to B at the rate of 8 liters per minute. Brine flows from B to A at the rate of 2 liters per minute. And brine is also drained from B at the rate of 6 liters per minute. Let X be the mass of the salt in kilograms in tank A at time t minutes. Let Y be the mass of the salt in kilograms in tank B at time t minutes. Find a system of differential equations involving X and Y. Again, X is the mass of the salt in tank A at time t. So dx dt is the rate of change in the amount of salt in tank A. We calculate dx dt just as we did in the section on linear differential equations. Dx dt is going to be the input rate minus the output rate because we're looking at the rate at which the amount of change, or we're looking at the rate of change in the amount of salt in the tank. So here's the input rate for salt in the tank. The rate at which salt is entering tank A is 2 liters per minute. We saw that down here because salt is flowing into tank A from tank B at the rate of 2 liters per minute, at least brine is. There's no salt that's entering here because that's just fresh water. And the concentration of salt in tank B is going to be Y kilograms over 24 liters. Multiply the volume and the concentration together, and we get 2Y over 24, in other words, Y over 12. And by dimensional analysis, the liters cancel, and we're left with kilograms per minute. So that's the rate at which salt is flowing into tank A. The rate at which salt is leaving tank A, the output, well, again, the volume is going to be 8 liters per minute. That's the rate at which salt is flowing out of tank A into tank B. And the concentration of salt in tank A is X kilograms over 24 liters. In other words, when we multiply that out, we get 8X over 24, or X over 3. So dx dt is going to be the input minus the output. It's Y over 12 minus X over 3, or if we put the X first, it's negative X over 3 plus Y over 12 kilograms per minute. Do the same thing for Y. Y is the mass of the salt in tank B at time t. dy dt is the rate of change in the amount of salt in tank B. And dy dt is the input minus the output. So the input rate, the rate at which brine is flowing into the tank, is 8 liters per minute, because we saw earlier that's the rate at which salt is leaving tank A and going into tank B. Really brine, not salt. Multiply 8 liters per minute by the concentration of salt from tank A, that's X over 24, you get 8X over 24, X over 3. That's the rate at which salt is flowing into tank B. What's the rate at which salt is flowing out of tank B? Well, the output rate is 8 liters per minute. Because again, you've got 2 liters flowing into tank A, and you've got 6 liters going down the drain. So a total of 8 liters per minute is leaving tank B. The concentration of salt in tank B is going to be Y over 24. Multiply it together and get 8Y over 24, in other words, Y over 3 kilograms per minute. So dy dt is the input minus the output. It's X over 3 minus Y over 3 kilograms per minute. So this is our answer. That's our system of differential equations for X and Y. Solve this system of differential equations. We can solve this using substitution. Since X can be expressed in terms of Y and Y prime, we have dy dt plus Y over 3 equals X over 3. Okay, so what we're doing is we're just getting the X over 3 all by itself. And we have dy dt plus Y over 3 equals X over 3. Yeah, I don't like the X over 3. We're going to multiply both sides by 3 and end up with X equals 3 dy dt plus Y. Okay, so there we've solved for X in terms of Y and dy dt. The goal here is to express everything in terms of Y and dy dt. Y and derivatives of Y. So let's plug this into the first equation, dx dt equals negative 1/3 X plus Y over 12. Okay, so notice, now we need to find dx dt. So if X is 3y dy dt plus y, to find dx dt, we just take the derivative of both sides. Take the derivative of, this side, we get dx dt. Take the derivative of this side, okay, and we're going to get 3 d squared y dt squared plus dy dt. So again, all we're doing, we already know x. X is this, 3 dy dt plus y. We're taking the derivative of x. In other words, we're taking the derivative of this expression. That's going to be our left side. So that's dx dt. And then on the right side, we have negative 1/3 x plus y over 12. Okay, so we know what negative 1/3 is. We know what x is. It's 3 dy dt plus y. And then we have plus 1/12 y. So we have rewritten this expression so that it doesn't have any x's in it. It's just in terms of y. So simplify by getting everything on one side. We get negative dy dt minus 1/3 y plus 1/12 y. We can simplify this. Negative 1/3 plus 1/12, that's negative 1/4. So we end up with negative dy dt minus 1/4 y. Okay, so that's what we've got on the right side. And this is what we have on the left side here. Okay, I don't like d squared y dt squared and dy dt. So we're just going to express that it's y double prime and y prime. So when we rewrite this equation, we have 3y double prime plus y prime equals negative y prime minus 1/4 y, right? Just look at this. That's what we ended up with at the bottom of the last page. Let's get everything on one side. We get 3y double prime plus 2y prime plus 1/4 y equals 0. Or, again, you know how we solve something like this. We jump to 3r squared plus 2r plus 1/4 equals 0. And then we factor and solve. I don't want to factor something with a 1/4 in it. Let's multiply both sides by 4. And we get 12r squared plus 8r plus 1 equals 0. That factors nicely. We've got 2r plus 1 times 6r plus 1. So either 2r plus 1 is 0 or 6r plus 1 is 0. In other words, r equals negative 1/2 or r equals negative 1/6. And in light of that, we know what the solution is going to be. So y is going to be c1, some constant, times e to the negative t over 2, plus c2 times e to the negative t over 6. Great. Well, that handles y. That's great for y. Now let's find x. So we have this formula for x, and we're going to use the equation on the previous page to find a formula for x in terms of t. So x equals 3 dy dt plus y. We need to figure out what this dy dt is going to be. Well, we found out on the previous page what y is. Okay, we've got this over here. So let's just take the derivative of both sides to find dy dt. When we take the derivative of that, we end up with dy dt equals negative c over 2, e to the negative t over 2, minus c2 over 6, e to the negative t over 6. So we're going to plug that in for dy dt. In other words, we're going to plug that in right over here. So x equals 3 dy dt, or 3 times this messy expression, that's going to go right over here, plus y. And again, we know what y is. We just found that on the previous page. We're going to multiply through by 3. We'll distribute the 3. We get negative 3/2 c1 e to the negative t over 2 minus, 3/6. That's a half. We know what that is. So minus c2 over 2 e to the negative t over 6. And then again, we get plus c1 e to the negative t over 2 plus c2 e to the negative t over 6. We can combine things. So notice the coefficient of e to the negative t over 2 is going to be c1 minus 3c1 over 2. That's negative 1/2 c1 e to the negative t over 2. When we combine negative c2 over 2 and 1, we're just going to get positive 1/2 c2 e to the negative t over 6. Okay, so this is our formula. So that's going to be our formula for x. Awesome. Find the system of differential equations if we start with 1/2 kilogram in tank A and 0.8 kilogram in tank B. Okay, so now we've got an initial value problem. So we start off with the expressions we just found a moment ago for x and y, and we plug in t equals 0. So x of 0, you plug x equals 0, or you plug t equals 0 into this top equation. You end up with this, but since e to the 0 is just 1, we end up with negative 1/2 c1 plus 1/2 c2 equals 1/2, because x of 0 is 1/2. That's what we were told a moment ago up here. And then y of 0, again, e to the 0 is 1, e to the 0 is 1. So y of 0 is just c1 plus c2, and we know what y of 0 is. You start off with 0.8 kilogram of salt in tank B. Okay, so now we just have a system of equations. Minus 1/2 c1 plus 1/2 c2 equals 0.5. c1 plus c2 equals 0.8. The solution to that turns out to be c1 is negative 0.1 and c2 is 0.9. So let's just plug those in. We'll plug those into these equations for x and y. Okay, so x is negative 1/2, negative 0.1 e to the negative t over 2, because we just found out a moment ago what c1 is, plus 1/2, 0.9 e to the negative t over 6. So again, all I'm doing is plugging in the values of c1 and c2 into the formula up top here. So that simplifies to x equals negative, or x equals positive 0.05 e to the negative t over 2 plus 0.45 e to the negative t over 6. And y is pretty simple. It's just going to be c1 e to the negative t over 2 plus c2 e to the negative t over 6. We know what c1 and c2 are. So we end up with y equals negative 0.1 e to the negative t over 2 plus 0.9 e to the negative t over 6. Graph the system. Okay, this is cool. These are parametric equations. Look at this. We've dealt with parametric equations. You learned about that in calculus too, forever ago. That was ages ago. So we can plot these parametric equations for x and y. Okay, these ones that I've got down here. So you can graph them in a graphing calculator. Make sure you're in parametric mode. So if you have a TI-83 or TI-84, press mode. Make sure this says parametric. If you've got a TI-Inspire, notice what you have to do. Okay, you've got on the menu, you've got graph, and then you have to choose parametric. Or you can just use an online grapher like Desmos or GeoGebra. That's what I did here. So here's what you get when you graph Desmos. The easiest way to graph parametric equations is just to express it as, basically, to express it as coordinates. So those are the parametric equations for x and y. And when we graph that from, let's say, 0 to 40, this is what the graph ends up looking like. Notice, this is where we started. So x1 was 0.5, and I'm sorry, x0 was 0.5, and y0 is 0.8, and that's the point we start off at. And then notice what happens. It cruises to 0, 0, which makes sense because you have fresh water flowing in, you have brine flowing out, so eventually the amount of salt in the tanks is just going to go to 0.